Hello everyone, welcome to Module 6, Session 1 of the ML Foundations. Our speaker today is Benjamin Cox, so if you have any comments or questions for him, please make sure to use the chat or the Q&A box. With that said, I will hand it over to our speaker. Enjoy the session. Ben?
Awesome, thank you. Yeah, and as Franklin said, if you have any questions along the way, feel free to toss it in the chat. I'm happy to answer what I know and give you a place to look for the things that I don't know. So today is ML Foundations Machine Learning Interpretability Session 1 with Driverless. So what does that mean? I came in and I talked, I think in the earlier section this summer, about AI foundations, about responsible AI. This is sort of kind of the technical implementation of that using our enterprise software, Driverless AI. So a lot of this is going to be done as a demo, and I'm just going to kind of walk through the software and show you how I might go about solving one of these problems and, on a customer. But I should give some context before we get there, because I'm operating under the assumption that most people, were in, last section, but I think it's important before we kick off again. So some background here is largely that, we do believe, as you can see by the way we structured our company, is that AI is kind of the future, right? Or the present, and will only get bigger in the future. However, I think everyone has seen these types of fail cases. And one of the things that has made adoption or trust in the industry kind of tricky is these fail cases that come up of kind of algorithms going rogue. And they're not always machine learning, they're not always AI, and they're not always even an algorithm problem. A lot of these end up being data problems, right? So it's our job as practitioners, to hold ourselves accountable to make sure that these situations don't occur, right? And the way that we believe that we do that is through responsible AI or interpretable machine learning. Now, the thing is that when we started this kind of adventure of explainable, interpretable AI, these terms weren't really defined yet, right? And so since we started, the suite is called machine learning interpretability, but the terms have kind of been shuffled around, right? So we see the larger bucket as responsible AI. And what we're kind of going to be using today is our interpretable machine learning interface. But a lot of what that does is actual explainable AI post hoc model analysis method. So, one of the leaders of the program who started this kind of product investment is Patrick Hall. And he brings up an interesting point of trust versus understanding. And a lot of times I talk about it, I'll go back, in that, they're kind of wanting the same thing, right? The more you can trust your model, or the more you understand your model, the more you can probably trust your model. But there's actually a different flavor of that, right? Like you can learn a lot about your model and decide that this is not a model that I trust, right? So our goal today is kind of go through a churn exercise and analyze all of the things that you might want to consider as a practitioner before you take this model to leadership, or before you take this model to your manager and say, okay, this is ready, let's put it into production. Because a lot of things on the surface might look good, but then, when you really get, start doing some post hoc analysis, start to think about what the story that it's telling you doesn't really, piece together, right? So one of the things that we talk about is like this risk iceberg, right? I think a lot of companies in their adoption of AI curve kind of think about two things, right? They think about those fail cases and the brand risk of, what if we make a chat bot and it ends up really racist or sexist or derogatory? Or just on the surface, we don't have the skills, right? So I think a lot of companies, they just go to these two major ones. But I don't think that enough consideration goes into the kind of risk management that comes with models that you might not see, right? Or the ethics and bias considerations that might be under the hood of the model that you're not really thinking about until you do some of these post hoc analysis methods, or some of these deep explainable, or just, exploratory data analysis metrics, or is my model hackable? Or have I built a model that is not really well thought through, and the minute, we shine a light on it or put it under a microscope, we realize we have a lot of technical debt because this model, isn't really, creating signal that we like, right? So this is the last thing I'll kind of share before we jump into it, right? I think this is kind of our current state thinking, right? The industry right now still sort of operates in a place where the area for interpretability, explainability, and review for fairness sits after you've built a model, after you've kind of done all the EDA, and right before you go into production, right? And there's some interpretability and explainability function in ongoing model management, but and we were actually kind of in the school of thought for some time too, but we have taken a different stance. We believe that the explainability, interpretability, and fairness focus should exist at every step of the process, right? And you can see in our suite of product that we built accordingly, right? I think that the question for fairness and the question for explainability or interpretability can start before you've even decided to build a model, right? Once you start to look at, distributions of data, unstructured data like NLP, imbalances, anomalies, outliers, data quality, that will have a tremendous impact on what kind of signal your model is going to drive. And it's important because you're not even to the modeling point, right? Like, I think there's like kind of this Pareto saying in the industry that 80% of your job as a data scientist, or 95% of your job as a data scientist, is data handling, and 5% is true machine learning, right? And I think there's some truth to that. Obviously, we try to build technology to shift that weighting, so you spend more of your time modeling and creating good models. But it's important to know that just because you've built a model and you ran a Shapley, your job's not done, right? If you have a model in production, you need to keep ongoing eyes on what that model's doing. Are features drifting? Are feature importances drifting? Are predictions drifting? Because a lot of companies will see that you can train something really, really nice in sample, and then when you get into production or out of sample, you realize that you've just overfit, right? And then this model is worthless. So these are all of the kind of things that we create and are creating in the end-to-end ecosystem of explainability throughout the machine learning model development lifecycle. We're not going to go through all of them today. So there's a question real quick. No canary is a way to control the model in prod. I'm not sure I understand that question. But there's a lot of different ways to kind of control models in production, and one that I'll kind of show here is, this is sort of what we propose, right? So we just published a book called Responsible Machine Learning. And one of the things that we talk about is a responsible machine learning workflow, right? So it's essentially this set of steps and processes that we believe makes a responsible machine learning workflow. And some of it is in model management and production, right? So once you deploy, we assert that there should be human appeal, there should be kill switches, there should be abilities to decommission, and then there should be real-time root cause analysis for these kinds of failures, and then start from scratch, right? So I won't spend too much time here because we're kind of going to go through this as it stands. I'll kind of walk through how I would do this live in production. But so this is kind of something that we put together, and I won't talk about this too much either, but I think it's important to understand that when you're building a machine learning team, that your goal is to be responsible or explainable, there's more than just technology, right? There's people and processes that go into it. And this is sort of just my take on it because I'm an ex-consultant. So I like to think about what does it mean for the people involved. And I think that's a really important thing that people don't consider that much, because in financial services, there's often like a CFO or chief MRM, and largely they're held accountable for the models that are being used at the company. And there's a lot of companies using machine learning that, should that model fail, there's not really anybody who's going to lose their job, or there's not really any data scientists whose feet are going to be held to fire, because it's kind of like a new, less regulated space, right? So we don't want that, right? Like, there should be skin in the game of practitioners to know that they can't make models risklessly, at least models that make it to prod, right? So let me check questions here, and then. Oh, okay. Canary model is a way to verify models. Sorry, I actually haven't heard of that method, but So we do drift detection in a couple ways, right? H2O, we've built a couple, and right now we started from a place of, okay, let's just look at prediction drift and data texture drift, right? Like, are we seeing more men in the out of sample data set than women? Or are we seeing more yeses than nos, right? But one thing that we're working on too is drift of explainability features, right? So in my opinion, the most important things that you want in production are, what are the ongoing Shapley values of features, in a model in production, right? Like that can be extremely valuable. So we're thinking about a lot of these different methods, and we're kind of all building this stuff real time. So let me stop sharing and pivot over to the actual driverless UI. Yeah, and so there's another question about H2O3 and interpretability. I don't want to spoil that surprise. To be honest, that's 2 days from now, and we just released a new package in H2O3 with a lot of new expanded interpretability features. So that's actually really exciting. The team worked really hard, and I think there's a lot of good stuff. One of my favorites, I guess I'll spoil this part, is that there's the kind of like Shapley weighting chart that I think a lot of people are really excited about. So let me share my screen again. All right, I hope everybody can see. So here's how I kind of set this up, right? Driverless is great because it really tees up a lot of this life cycle for you. So let's do this. Let me actually go back. So let's start from kind of the top, right? Let's take telco churn data set, right? This is a Kaggle data set, which I will show you kind of how it looks. It's really, really, and this sounds so basic, and I hate to say it, but it's really important that before you ever start modeling, you have a good idea of the texture of your data, right? Like if you don't it's so tempting to just get a big data set and just immediately throw a model at it and see, oh, do I have signal or do I not have signal? And it's a very, there's a lot of moral hazard with that, right? So in this data set, we're essentially trying to predict, will a telecom customer churn, right? And so right at the gate, you want to see things like, certain fairness metrics that might be kind of a flag in finance, like, gender, marital status, other, that kind of stuff. We're seeing a good split here, which is likely not going to mess up the weighting too much. One thing that I can see off the bat is that they flag senior citizens, and there's a smaller population of them. There's only 1,000, so maybe that could have an impact. We see the tenure sort of bimodal, right? There's a lot of very young tenure, and then there's this big pocket of long tenure. So that could be interesting. I don't know what to make of that yet. Multiple lines, it seems kind of a normal split. Other is a smaller one, so we might see some interesting flags there. And then you start to get into these kind of business questions, right? Internet service, online security. Like, will these kind of matter? And you've got fiber optic deals. So we might be able to get some nice intuition about like which services that does this telecom do well, or which do they not do well. So with that being said, let's kind of jump into it. Sorry, I got to answer this question. Okay, so the question is, what do I mean by signal? And signal is essentially saying predictiveness, right? Signal is saying if there's signal in the noise, we can actually make some sense of this data. Okay, so the data set we're doing is telecom churn here. And before we get into the model, let's kind of just review. And the reason I showed it to you in Kaggle is because usually you want to have some kind of data dictionary that says, okay, we understand, this is what this feature means, because sometimes you can see distributions, but you don't necessarily know what the categories are. But Driverless does a really good job of telling you male, female, senior citizen, 0, 1. And let's see if it kind of looks similar. And it appears that this data looks largely good. And so we can see that monthly charges, there's this, really high, low spike of probably users with next to nothing billing, and then sort of maybe a normal distribution here. And then total charges, this sort of makes sense, right? Like there's going to be a lot more people who haven't paid that much in. And then we see that the net target split is 73%, not going to churn, 27% yes. Right. And so these ones might be interesting too, month to month in contract. Like the intuition, I think, would be that less people with longer contracts will churn, right? That's kind of an assumption as a domain expert I might make, right? So, and one of the things you can do here too is if you have, and so a great example that comes up a lot is like AML, because the data is sometimes really imbalanced or the features sometimes can come off as very weird or have some time series aspect to them. You might want to actually incorporate what we would call like a data recipe. So like a pre-processing recipe to like group or flag or rename or, take the log of certain features, if we know ahead of time that those features are going to be there, and you can kind of just like add them in as a URL, or you can kind of live code it in, right? So what's really great about this is we built a no code environment for, pretty premier machine learning, but should you want to drop in a certain group by function or, some log function, you can do that as well. Because we want you to be able to kind of be fully extensible, right? And then you can go and dive in specific rows and see if the data looks like you might want it to. All right, so that being said, let's kind of go back. Let's take this data set and, again, one of the things you want to do before you even get to modeling is sort of understand, what the texture of the data looks like, right? So we can do kind of skewed histograms and see what the distributions are. We could check a correlation graph and see, there's a lot of highly correlated features here. So there's going to be some pockets of customers that look kind of similar. And that's fine. That happens a lot, right? And then you can see some features are very uncorrelated, right? Not negatively, but uncorrelated, right? So, and the thing is too is, for visualization, people have a lot of different types that they want. So in these types of instance, you could do a quantile, you scatter probability, depending on what you're trying to get done, right? And that's just kind of trying to be flexible, right? And you can kind of take some recommendations and see if certain transformations make sense, right? Like taking logs and other things, right? So let's actually get to the prediction and MLI component, right? Like I think we want to spend the bulk of the time there. So the way that we kind of do this is pretty simple, right? Let's do the following. Let's kind of split this in normal machine learning exercises, right? You have like a training and test set. So we'll do train 2, test 2, random seed is fine, target column, we could say churn. And usually you want, I think the industry standard is something like 80-20 still, or 70-20-10, right? So this will be fine. We'll do save. And here, let's predict. And so the training data set will be train 2, live demo, test set, test 2. Let's do target will be obviously churn. That's just a binary classification. 0 equals they didn't churn, 1 equals they did churn. And in this situation, we can drop certain things like customer ID, gender if it matters, and these kinds of things, because a lot of like best practices, I would argue, is deleting certain features, right? Models get smart. There's a really good example that comes up in credit all the time that Scott Lunderberg gives on Shapley values, and we'll kind of talk about what that means. And in this example data set, they see that this person with 50 years of credit history is actually getting flagged as a higher risk. And what they realize is happening there is the model is using years of credit history as a proxy for age. And that's not a variable that can be included. So, they might not lend credit to somebody who's retired who has no net new income, which kind of makes sense. But, we're not sort of allowed to make decisions based on that in financial services. So I'm going to, make this a very low amount of time. I'm going to keep interpretability quite high. And I won't care too much about accuracy on this one. That's not really the goal here. There's no time column, so this is not a time series problem. And then for, kind of what you're trying to predict, it depends, right? Like, I think that depending on what you're trying to accomplish, certain features might matter more, like pure accuracy might matter more, AUC might matter more, F1 score, but we'll use AUC here, right? So let's make sure we've dropped the right columns, done. And then let's just launch this, right? And so what starts happening here is with driverless genetic algorithm, it basically has a universe of models that it runs through and tries to solve, right? So what you'll start to see is you'll start to see models getting tested, and I'll show you what it looks like, right? Because I've run a few practice experiments. If there's any questions, let me know. I think my computer might be freezing, so in the interim, I'm happy to answer anything that people are thinking at this point in time. All right, so my instance just failed. I think I was running too many experiments potentially, or need to refresh it. So just bear with me for a second while I get this set back up, and I'll fire this instance back up again. Might take a couple minutes. So in the interim, I guess let me pivot back. I can kind of share a PowerPoint while I get reloaded here. So what I was sort of talking through was this idea of building a responsible machine learning workflow. And I think what we kind of walked through so far is, this function, right? Analyzing your data, kind of checking for fairness, things that might exist on the front end, doing exploratory data analysis, picking our benchmarks, whether it's, AUC or something like that. And then actually talk about interpretable features when I reset this experiment up. So I can show you kind of some things that I would do personally, right? I think that, we've built an extremely, extremely smart machine. It's almost too smart for a lot of regulators, right? So a lot of times I'll try to really simplify it down and say, some of these features might be a little too complicated. And it's not that they don't provide, actual signal. It's that they're just hard to interpret, right? So we have a lot of different, like, really, really well-designed automatic feature engineering that goes on, and that's a big, big pain for actual data scientists. And I think any of the folks in the crowd who do data science know how much time goes into kind of creating, iterating through new possible features to see if they actually add any signal or if they just kind of double down on similar signal that existed before. But what we're essentially going to do, and I can reset this experiment up, is we'll create a universe of constrained, fair, interpretable private models, and let it run through the calibration, right? And then we'll go through assessment. We'll talk about explaining it, how we might debug it, think about discrimination, and then think about the risks and show kind of human review and documentation, as well as monitoring, and then sort of talk about what, the post hoc analysis post period, where we're talking model ops, model management, would sort of look like. Right. So while this is, let me do something else. Let me give you a counter example while this continues to load. So last night, I wanted to build like a really complicated counter argument. So what I did was I took driverless, and one of the things that we do is we create automated model documents, right? So once you created a model, you can just click export and get a really robust write-up of what went on in the model. And since I'm creating this whole argument that you should be aware of unnecessary complexity, align with simplicity, and lean into transparency, I wanted to build the counter argument, right? So I think the one, the popular way to look at things are like TensorFlow and deep learning, right? So what I did was I constrained the universe of this problem to just TensorFlow, and it could be as complicated as it wanted in terms of features, in terms of depth, in terms of everything, right? So ultimately, we got an internal accuracy of 85% or AUC of 85%, 85. And then on the test data, it actually went down a little bit to 0.828, right? So those numbers don't matter too much yet. 1 second, starting. Okay, so the settings I had it on were high accuracy, medium time, interpretability. Basically no interpretability, didn't matter, right? So I'll walk through kind of some of the things that this model found important and how it was built, right? So it's worth noting that this took a lot of time, right? Like deep learning is pretty computationally intensive. So it tried all of these various models, right? Like it tried a bunch of different activation functions, LU, TAN, CELU, all of these on TensorFlow, right? And this is kind of the feature evolution over the iterations and, what kind of accuracy they were able to get to. And so it used a lot of complicated features, right? So I'll show you here, a lot of the features that it was using were cross-validation target encoding, cluster distance, and it created a lot of these, right? So, if you kind of think about it, these are combination features that are doing interactions or relationships between multiple variables, and it gets a little harder to explain, right? Like I think that, one, if it's just a cross-validation target encoding payment method, one of the payment methods, it's not that big of a deal. But, we're talking about a cluster of monthly charges, senior citizen, total charges, and tenure. That's like a 4-feature cluster, right? And it gets a little trickier to explain to regulators when this happens. So, okay, now I'm going to jump back to my instance and kind of walk through an experiment again. And so I guess I should make a point here that I think is kind of critical. I think that one of the things that gets lost in all this is industries search for silver bullets, right? Like I think that a lot of times, we look for things like, so Shapley value, values, which we'll get to, are kind of gold standard for this type of stuff. But what that doesn't mean is that if you get Shapley values, you're done, right? I would argue that it's really important for folks to understand that there's multiple ways to analyze models post hoc. And it's important to kind of go through them all and check and see if they're kind of telling you the same story, right? As a data scientist, your goal is to kind of like unwind be an investigator and unwind the story that the data is telling you. And it's important you look at it from multiple angles, or else you can kind of trick yourself into believing something that you maybe shouldn't, right? So in this instance, because we're kind of time constrained, I'm going to kind of lower these because I just don't care so much. But what I will do, and what I'll show you, is kind of something that we should aim to try to do, is start to think about. So I kind of described those maybe more confusing features that might have existed. Because this is kind of like an intro class, what we'll do is we'll turn off target encoding, we'll keep one hot encoding, we'll remove some of these more complicated features, right? I think that's fine. And how much signal they added, we'll sort of find. And then what we will also do is we're also going to constrain the universe of models, because I don't want any deep learning or super complex models to exist in here, right? So I'm going to turn off PyTorch, turn off TensorFlow, and keep the rest. The rest are pretty simple, right? And then I'll actually take ensembles out. So I'm not sure if folks here are familiar, but ensembles are just series of models stacked together to increase predictiveness. And the problem is when we create decision trees to explain what kind of rules the model is creating, like soft machine learning rules that it's creating, it can make it a little more complicated. So I just created a very simple universe of models here, right? Of models and features, and we're gonna fire this up and see if we can't get close to that, multi-hour deep learning exercise. So what happens is it immediately starts ingesting the data. It starts detecting the column types, whether it's integer, Boolean, continuous, unstructured image, you name it, right? And it'll start kind of tuning the modeling backend, start creating features, and start putting some tests on the board. Now, I guess what we should do here is let's pivot over to the actual MLI UI from another experiment I did. In this one, I did simple features as well. And this is the kind of end result, right? In data, so let me actually download this R report. I basically constrained it so that there wouldn't be any clustered or target encoding features. It would just be kind of simple transformations. So let's download this report real quick and see what was the net accuracy. So in this one, 0.854 and 0.825. So I think that this very simple model compared to a very long trained TensorFlow model only lost 0.003% accuracy, if I remember correctly. All right, let's check that. And in this case, we don't know what the cost function of losing this customer is, but this might be a trade-off a business owner is willing to take, right? That's an important thing to note. Right? So let's kind of analyze what this model looks like, right? So let's take a peek. I'll pull it up in the text format. So in here, we can see that, it tried a bunch of things. It kept very simple features, no transformers, or just a frequency encoding, right? Like, how much, some of these work. And then, one hot encoding, which is just taking a categorical and moving it horizontal. So we can say one category of this is a certain level of importance. So this model looks pretty good. I think we like this a lot, right? So let's jump into MLI and just kind of start tooling around, because I think that's what we want to discuss here today. And so from here, you pretty much just click interpret this model, and it'll start spinning things up, right? And there's a lot to take in here. So we're going to get through it. We're going to kind of talk about it all, and then I'll open it up for some questions, because I think that this area can get kind of heady. So let me start by saying, if you find yourself confused, don't worry. I'm something of an expert in this space, and I still have to go back and rewatch or reread the math, because this is a particularly nuanced area of artificial intelligence, right? We're fitting simple models to complicated models. We're doing pretty heavy algorithms to simplify features and understand features. Just know that if you're kind of scratching your head, that's normal, and there's some nuance to machine learning interpretability. So don't feel bad. Stick with it. This is important stuff, right? So original feature importance is a lot of what you're going to see in industry. So contract length, type of contract, 2 year, 1 year, that's kind of something that we thought about, and it makes a lot of sense. Tenure, we don't know which direction this is yet, but we do know that tenure matters. And then monthly charges, online security, internet. These make sense, right? Like these on the surface make some amount of sense, right? So that's naive. That's just features that have been untransformed, right? So let's actually take the results of the feature engineering and think about it and say, okay, transform feature importance. We believe that this is kind of the low bar of monthly charges, and that might make sense, right? If somebody's not getting billed, or getting billed a very small amount, and their account is some kind of legacy account that they haven't shut down yet, they might be more inclined to shut it down. A certain level of tenure appears to matter. And then we're going to kind of get into what this looks like, right? So we're going to come back to that. We're going to unpack that a little bit more. But while we're here, let's talk about Shapley, right? So this, I mentioned this is kind of a gold standard in machine learning interpretability. This looks just like feature importance, right? And that's a fair interpretation to make. What Shapley values are based on a game theory strategy or game theory math equation developed by Lloyd Shapley and kind of rebrought to the surface by Microsoft Research, and a couple of others. There's been a lot of new Shapley developments, right, or resurgence in Shapley. But what what Shapley values assert is that depending on the order that you stack features in, they have different levels of importance. Now, I know that might be hard to understand, but just understand that if you have, a customer where you start to do the math, you go contract tenure, internet service, online security, the way you weight those features might be very different from online security, internet service, tenure, contract. So what Shapley values aim to do are millions of calculations in the back end that essentially get the net average of these features in all orders, right? In all permutations of stacking orders of feature importances, right? So it's important to know that you're talking about whether it's local or global, you want to know how important a feature is generally, not just in the order that it's processed, right? So Shapley values are kind of a gold standard of machine learning explainable AI methods, right? And so transform Shapley, we find that this one tenure feature is really, really important, right? Overall, no matter what the order is. So let's take tenure, right? And let it be known that average prediction, the higher it is, means the more likely it is that somebody will churn, right? So we talked about contract. So month to month we see is the highest average prediction. That's intuitive, right? If you're month to month, you are probably more likely to leave a service provider than if you're locked in for a 2-year contract. I think everybody would agree that sort of makes some sense. So we can see that from a PDP, partial dependency plot, this feature importance kind of makes sense, and we can feel kind of comfortable that contract is being read right. So let's check tenure, right? What's interesting here is that I actually, I like this example a lot, right? Because we see that, obviously the younger customers are more likely to churn or have higher average predictions, and it sort of smooths over time. And it's kind of thinking, the intuition is kind of, yeah, I mean, the longer you've been with a company or been with a service provider, probably the less likely you are to leave it. But what's really interesting is that there's this weird spike at 72. And normally we might want to constrain it so that, if, and this would be called monotonicity constraining, right? So the further you go, the feature weightings can only go in one direction. So you don't have this kind of like nonlinear feature weighting across a universe of features. But what's interesting is some scenarios of non-monotonicity constrained features can tell you some interesting things, right? Like, so sometimes you'll see this with tenure of 60 months or 5 years, where there's some kind of lock-in period that existed. And that the minute these people, these customers reach the end of some lock-in period, whether it's 72 months in this case might be, and we don't know this, right? This is where we'd like to go back to that telco and say, hey, we see this interesting spike of attrition at 72 months. Do you have any explanation for that? Like, is there any reason that might be the case? There's 2 explanations for this, I would argue. One would be that there was some 6-year lock-in, which seems kind of weird, right? And then there's the other side of it, which is, this 72 tenure bucket could represent all 72 plus, right? Like I remember seeing that this tenure feature was bimodal, and there was a second spike at the high band. So this is one that you'd want to just bring in domain experts and talk about what that sub feature category means, right? So that's partial dependency plot. Then we want to talk about fairness, right? This is really important, and I think this is what a lot of people care about. Essentially, the way that we do, checking for sociological fairness or discrimination or disparate impact, as we call it, disparate impact analysis, is through these DIA models, right? So in this case, we don't really care if somebody is discriminated against based on how much tech support they received. And because gender is very top of mind, let's take this. And usually the reference level will be, the class that you will believe might be, favored by historical bias, right? In this case, we don't see any disparity here, right? We're not seeing, and one threshold that comes up a lot. So if any disparity was flagging here, based on our 1.25 or zero point 0.8 threshold, we would see it. It would be highlighted in orange. So this is pretty good, right? Like you know, you don't want your model kind of discriminating against women in predictions. So I have a hunch, right? I have a hunch that we might see some disparate impact on age on this senior citizen feature, right? So yeah, see, we're seeing that it's not passing fairness here, but let me caveat that, right? So, you know, you can see a group disparity that we're seeing an adverse impact hitting senior citizens here of our prediction that they might churn. But one thing that happens a lot, and this is really, really important to note, is that a lot of times disparate impact can be triggered by a lack of population, right? When you have a split of 50% men and 50% women, it's likely that your statistics are going to kind of come out the same. But when you have these disproportionate population weightings, you might just not have a big enough sample size to really know if, you know, every time you get it wrong or, you know, potentially create some adverse impact for a senior citizen here, it's going to show up a disproportional amount, right? So there's some combination of weightings here where we see like 35%, you know, 0.35 for non-senior citizens and 0.6 for adverse impact, but there's a much lower population. So in this one, you know, we don't want to do too much with it yet. We don't want to make too many assumptions, but we essentially see this and it says, keep an eye on this, right? Like you're seeing some disparate impact in the predictiveness of the model, but a sample size of 914 is not a great amount, right? That's not what you're kind of aiming for there. So let's do this. Let's do a couple things. That being said, we can quickly go to the summary and kind of do the experiment overview and say, okay, model summary, we're seeing the validation AUC is kind of 0.85, test AUC 0.82. You know, we're getting the model statistics, right? And then we can see that certain monthly charges, tenures, frequency tenure are kind of the most important features. And then essentially what we're doing in surrogate model summary is we are fitting simple models to complicated models and determining how much of the R squared or explanation we can kind of justify with more simple models, right? And we're seeing like 0.9, 0.99, and this is good, right? If we can fit a very simple random forest or very simple decision tree to represent a good amount of the R squared or the predictiveness of this model, that's good. You know, we're not over complex, you know, we're not making it overly complex, right? So let's actually show you what that decision tree looks like, right? So essentially, when we display this, we're kind of showing a decision tree that the model traverses to come up with the prediction, right? So there's really two tails of this that we care about. There's one where we want to know where the model is thinking is the highest likelihood of somebody churning. And then we also sort of care about where's the lowest, right? So in this example, we can see if you have a 1-year, 2-year contract, you kind of get pushed to this left-hand side. If you have no internet or DSL, you kind of get pushed to the left even further. And then if you have a 2-year contract, you'll be in the lowest probability of churn bucket, right? So if you have those combination of features, you're a very low risk of churn by this model. Now, however, on the converse side of that, sort of how we talked about, right? If you go month to month or no contract, you're getting pushed to the right. If you have no online security or it's not applicable to you, you're getting pushed to the right again. And then if you're under 3.5 months of tenure, you're also getting pushed further to the right. So if you're a young customer with no internet or no flag for online security and you're month to month, you're a very likely candidate to churn, right? So you really care about kind of how you get sorted through this tree and what that means for your, you know, likelihood of churning in this example. Now, what I think is really great is we can do a couple of things, right? What we can do is we can download all of these things, right? I think we built all these tools so you can kind of interface with them and play around with them. But what's really great is if you're, and this comes up in AML a lot, right? Like, so a lot of customers, like think of telecom, they'll say, oh, well, we don't want a living, breathing machine learning model, like running churn, right? But what we are okay with is a point in time machine learning model developing a nice savvy rule-based system for us, and then us implementing that in whatever systems that we use, right? So what you can do is you can download these surrogate decision tree, rules-based systems in Python or .txt and export them and be ready to go. You can plug this into most engines pretty simply, right? And the code is ready to go. I think this is one of the best extensions we've put out recently, because a lot of companies aren't yet comfortable with full machine learning models living and breathing under the hood. But if you can get a machine learning model that puts together a really well predicting rule-based system and have all these stakeholders sign off on it, they're comfortable putting that into production. That's much more comforting for certain companies, especially in regulated industries, right? Because sometimes model approval processes are pretty heavy, right? So I think this is one of our best features, right? And then one of the other things you can do too is you can kind of check K-LIME. Like LIME stands for local, interpretable, model agnostic explainability, I think. And essentially what we want to be able to do is, and you can do this locally or globally, right? And some of it is cluster-based, but we can kind of go to top positive global attributions, internet service, fiber optic. We could see a direct correlation of 0.06, contract month to month, higher churn, payment method. And so all of these sort of make sense, right? These are all the things that we kind of, saw in the tree, saw in the PDP, saw in the SHAP values, right? And you can export these, right? Like reason codes for a lot of companies are really important. I know I've been on multiple projects in the history of my career where all they wanted are root cause or reason codes for each prediction, right? And that matters tremendously. So to be honest, there's a lot more, and I want to be conscientious of time. The last thing I will show you, and this is sort of kind of the ultimate data science sandbox, is the idea of sensitivity analysis, right? So you'll often hear it described as what if, and it's essentially giving you a sandbox to say, okay, I've got all of my predictions, we've got my cutoff, and we see that 0.3208 is the threshold for F1 before it gets bucketed in one thing to another. So what if we said, what if we actually changed, let's not do that one. Let's do, what if we changed all of the tenure to 60? What if we made everybody, 60 month tenure? Now let's rescore it and see what that did. My assumption is that it might dramatically decrease the amount of customers that we predict will churn. Yeah, so that's exactly what we see, right? We see a big percentage change in the amount that, in the overall mean, right? We're saying that if all of our customers have been with us for 5 years, they're going to churn a lot less, right? And what this also gives you the ability to do is sort of key in to specific customers. If the threshold is 0.32, we say 0.35, this might work, this might not. You can sort of filter down and isolate, customers on the edge, and then say, okay, now what could I do to that customer, right? Could I take this person who's right here? All right, let's take this person, right? So when you click it and you get this specific line item, this person we don't think is going to churn, right? They're over here. What if we changed their monthly charges to 200, or let's change it to 0 and rescore? We might see them shuffle a little bit. And so that didn't do anything net to the data set, which is fine. But essentially and this one, there's a lot going on here, but essentially you have a full sandbox to filter on false positives and other features, right? Because I think what data scientists crave, and I know this was true for me, is once I've built a model and I've made all of these predictions, all I wanted to do was analyze false positives, false negatives, the clusters of information that might exist with these customers. And I can't stress enough, I know all data scientists have sort of kind of deadlines and benchmarks and turnaround times that they need to hit. But anytime I think you can invest more of your effort into really understanding the nuances of the model, you know, you're going to create a ton of value, right? And one of the cases that I'll argue for is that, you know, in finance, right, there was this digital banking boom where we realized that, like, you know, actions made by customer accounts was like one level of insight, right? Like, did they do a transaction? Did they buy something? You know, what have you? But then also digital banking platforms learn that, you know, the kind of metadata of how long are they on pages, what was their click-through rate, you know, what kind of products did they survey, you know, added a ton of signal as well. I would argue that the data that you create in machine learning, interpretability, and explainable AI is that same metadata of machine learning and creates signal as well. That's why I care about things like Shapley value drift or feature drift, right? Because it's important to know how your model is growing over time and what are the things that are becoming more or less important, right? So with all that being said, I know I've just covered a lot, and you're going to get a lot more of it in 2 days in the H2O, in the H2O3 section. That's about all I wanted to get through. There's actually so much more that we could get into. There's just no way we could do it in 1 hour driverless because we've built so much. But let's actually go see what our first experiment that we built did. And, you know, this one turned out really well too. Quite simple, only got 0.02% worse, and is a very simple linear model, or not linear model, but light GBM model that we can explain and probably get through regulation, no problem. So that being said, let me just leave you with a few closing thoughts, and then I can open it up for a couple questions. Got about 5 minutes left. The goal here is pretty obvious, right? You want to decrease the risk you take on with machine learning. I think you should understand when you deploy machine learning models, what is the volume, velocity, and materiality of that model? Are you making billions of dollars of predictions? Are you making hundreds of predictions a second? You know, the frequency and the scale of the predictions matters tremendously in how you're going to deploy this model. Obviously, increased transparency. Everybody wants to be able to understand what's going on inside the black box more. You know, technical debt is a big one. I don't think people consider, if you build a machine learning model with, you know, popsicle sticks and scotch tape, you are just creating problems for yourself down the road. Build yourself a stable, robust, dynamic model infrastructure that will enable you to kind of adapt and not have to start from scratch every time somebody says, well, we can't explain that, you know, throw it out. And then getting a deeper understanding of your data, right? This is level 2, level 3 information that is really giving you insights to your customer, right? This stuff is so important. And when you get to be able to algorithmically identify there's something fishy going on the 72-month tenure bucket, that's some insight that you wouldn't see if you were just scrolling through Excel, right? This is deep insight that, you know, companies want to know if, you know, their credit scoring, like, our credit history is a proxy for age, and then they're essentially being ageist in their predictions, right? And then increased agility and resilience, right? Like, the case for machine learning is that it evolves over time, and then it makes you faster to respond versus having to start from scratch and build a new statistical model. That's the value prop of learning, right? Is making sure your systems kind of evolve over time and get better over time. So take advantage of that, right? Like, build models that increase your stability, increase your agility, and make you more resilient for, you know, anomalous periods of time, especially in the era of COVID. Okay, so I've got about 3 minutes left. Let me take some of the questions. Okay, so there was one earlier about how much disparity would be strong. There's a rule of thumb, and I say that in very heavy asterisks, that like 1.2 or 0.8 essentially a 20% disparate impact increase over the, you know, the reference class is kind of like an operating number these days. I think we're still kind of defining, you know, and H2O just worked with Discover to write a paper on this about what is disparity, what is discrimination. I highly recommend people look at that. I could pull up the link or share it somewhere. But 1.2 and 0.8 tend to be really important, or at least kind of like what's operating in the industry. And then why prevent technical debt? So Google put out a paper that let me not mess this title up. Machine learning is the credit card of technical debt, I want to say. I'm not sure if that's exactly what it is, but essentially building flimsy models only creates work to do down the road. Not only because you'll have to rebuild those models, but because you'll have to unpack all of these predictions you've made under kind of suspect assumptions. So what I'm proposing is that if you build more stable, simple, resilient models, there will be less rework to do under the circumstance that, one, your company decides explainability matters, or two, your company has been reached out to by an oversight or regulatory authority saying, hey, your machine learning practices are not sufficient. Yeah, okay, let me actually pull up this paper real quick, and then I have to jump. So bear with me 1 second. I'm gonna drop 2 links into the chat for folks. One is the book we just published on responsible machine learning that kind of encompasses all of the things that you've seen here today. So the book is there. And then I also wanna share 2 more things. One, this is a paper that we wrote with Discover around transparently increasing access to credit and using machine learning to prevent disparate impact in credit decisioning, i.e., instead of discriminating against protected classes when they apply for credit and access to capital, how do we use machine learning to not perpetuate this bias and then to strip it out? So then I'll also put out a paper that we did around potential regulations and frameworks that are appearing across industry in different countries. Okay, Franklin, I've got to jump. Everybody who joined today, thank you so much. Really appreciate you guys joining, and really happy, you guys are interested in this stuff. We care deeply about this, and we're super, super enthusiastic for everybody who jumped in and took the morning to learn today. All right, thank you.